Okay, so on Tuesday we started studying this new force that we observe in nature, this new phenomena that we could use to lift stuff. And we said that, okay, there is this thing that we call the charge, and that if two objects are charged, if we have a charge over here, let's say its charge is Q1 in certain units, and we have another charge over here, let's say Q2 in the same units, then these two charges exert a force on each other. If we call the separation between the two as R, then the force that the first charge feels due to the second charge will be just some constant Q1, Q2 divided by R squared in the, let's say, R12 hat direction, where R12 hat is R1 minus R2. This is how we had defined it. R1 being the position of charge Q1, and R2 is the position of the charge Q2. And then we were discussing about the conductors and insulators. Well, now we have this microscopic picture that we know that everything is made up of atoms. The atoms contain the electron, protons, and neutrons. Protons are positively charged, electrons are negatively charged. So the net charge of an object is nothing but the total charge of the protons plus the total charge of the electrons. Since if electrons are negatively charged, if the number of protons and electrons are the same, we know that the object is neutral. And by rubbing two different materials, depending on what we call their electron affinity, their tendency to capture an electron, one object can acquire the electrons from the other one. So this is how we charge an object, by rubbing them on each other. Now we had if you remember, we were discussing about the electroscope, and we said that, okay, if this is the top of our electroscope, which is a conductor, and here if we put some material, and here we have the foils, if we approach some charge, let's say positive Q, now what happens in this picture is, if this is a conductor, the electrons will be free to move. It's a solid, so the nuclei cannot move, but the electrons will be free to move. If the positive charge approaches, we know that opposite charges will attract each other, so negative charges will accumulate over here, and positive charges will accumulate on the foils. And since the foils, they both have the same charge, they will just push each other apart. Of course, if this is not a conductor but an insulator in which the charges cannot move, then the foils, nothing will change in the foils. This part will be negatively charged, this part will be positively charged, but all of the charges will be just stuck over there. Now, any questions up to here, up to this part? We have the insulators. We have the conductors, and we have what is called the semiconductors. And all of our electronic technology is basically based on these, what we call the semiconductors. The most common semiconductors are the silicon and germanium. Of course, there are other ones. Well, as the name implies, they are kind of midway between conductors and insulators. We know that in conductors, there are many free charges that move around. In an insulator, there is no free charge to move around. In a semiconductor, there are just a few charges to move around. So in general, they have a very low conductivity, but nevertheless, their properties can be significantly modified by just adding some other materials in it. By just mixing them with other materials, then we can change the properties of the semiconductors, which allows us to build all these different kinds of electronic equipment just using these semiconductors. But this semester we will be mainly interested in conductors to conduct charges and insulators to save us. Now let's go back to this force between these two charges. We know that this is the force law between 2 point charges. Then the question is, what if we have more than 2 charges? What will be the force in that case? So let's say that we have one charge over here, Q1, another charge over here, Q2, a third charge over here, Q3. Let's say that their positions are, this is R1, this is R2, and this is R3. So we just choose some coordinate axis to specify the positions of the charges. Now the question is, what is the force acting on the first charge? Now again, from experiment, we know that this force acting on the first charge, or you can also do it for the second charge or the third charge, is nothing but the force acting on the first charge due to the second charge plus the force acting on the first charge due to the third charge. If you remember when we were studying gravity in mechanics courses, we also had this principle that if you have more than one sources of force, then the net force acting on each one point is nothing but the sum of the forces that the other points would create independent of the presence of the third one or the fourth one. So if we write it down, this is 1 over 4 pi epsilon 0, Q1, Q2, R12 hat, divided by R12 squared, plus 1 over 4 pi epsilon 0, Q1, Q3, divided by R13 squared, R13 hat. So this is the force acting on the first charge due to the other charges. This is what we call the superposition principle. We just add the forces. Now this is, for example, for relativity, for gravity, sorry, the superposition principle is only approximately true. It is true to a large approximation in the solar system, for example. But if you go, I don't know, to some black holes, if you study the black holes, the superposition principle will not hold in that case. But for electrostatics, as far as we know, as far as all the experiments that tell us, the superposition principle holds exactly. It's not an approximate thing, it is exactly true. Now, if you look at this force acting on the first charge, this is all over 4 pi epsilon 0, Q1, Q2 divided by R12 squared in the R12 direction. Now, the force is a vector quantity, so when you are adding these things, make sure that you pay attention to their direction also. Q1, Q3, now R13, R13 hat. Well, both of them are proportional to Q1. 1 over 4 pi epsilon 0 plus 1 over 4 pi epsilon 0 Q3 divided by R13 squared, R13 hat. Okay, this is our force. So just imagine we have these two charges somewhere, and we bring some other charge over here. So it can be Q1, you can change it, but whatever charge you bring, the force will be proportional to this quantity, which doesn't depend on the properties of the charge that you bring, multiplied by the charge that you are bringing, so-called the test charge. Now, this quantity over here is something that is related to the other charges of your system. And this quantity is what we call the electric field. Yes. So this is what we call the electric field. Now, why do we define the electric field? Now, one problem with this expression, with this Coulomb law, this law, it kind of assumes that the second charge influences the first charge from a distance. This is what we call action at a distance. Well, it is something that in physics we don't really like. I mean, as far as we know, all the physics, the nature is, we say that it is local, in the sense that I am only influenced, anything is only influenced by things that are in the very near vicinity. I will not be directly influenced by the presence of Serjan over there. I will be indirectly influenced by him. He will be sitting there, he will be reflecting lights. The light that hits him will be reflected in my direction, and when that light reaches me, reaches my point, I will be influenced by that reflected light, not by him. Now, just like that, we don't like the concept of this charge influencing this other charge directly, but we invent this electric field concept. So in this electric field concept, what happens is, if you have, let's see, we have these three charges, Q2 and Q3. They define what we call the electric field that covers all of the universe. And when you bring some charge over here, the charge over here only feels the electric field at that point. So if you look at this expression, now this expression is in fact the electric field at the point R1. So the force that the first charge feels is nothing but the charge, its charge, times the electric field at its position. So the force is again created, the force that the first charge feels is again created by something at the position of the charge, not by something at a faraway distance. Questions? Of course, for the time being, it just seems just a redefinition of the things. I mean, you say that, okay, the electric field at the point R1 is directly created by the charges at the point R2 and R3, which are at a faraway distance. So how does this resolve our problem? Now, we will see towards the end of the semester, okay, that is one problem. Is the electric field at the point R1 created by charges at a far away? So how does this resolve the issue? This is one thing. The second thing, is this just a mathematical construct, or does the electric field has any physical significance? Does it really exist, or is it just something that we invent? Well, let's look at this expression of the electric field. Now, we know that everything is made up of electrons and protons and neutrons. So everything is made up of point charges. So whatever charge distribution you can imagine, there will be just a bunch of point charges. The number of the point charges might be very huge, but nevertheless point charges. So if you have many point charges, the electric field at any point will be just given by the sum of not two terms, but many terms. Now, if you look at these terms, all of them are quite continuous. So the electric field will be continuous. There are some cases that it will not be, but we will cover them in a week or so. Yes, that's a good question. It turns out that it does take time. So that is why we like this concept of the electric field. So the question is, what happens if you change the position of charge, let's say Q2? Now, this definition of the electric field, again, tells you that at the moment that you change the position of the charge Q2, the electric field at the point R1 also changes. But we will say that, I mean, currently we are just looking at electrostatics, so we don't really have any moving charges in our system. That is the first assumption that we did on Tuesday. Currently, we are only studying electrostatics, and Coulomb's law is valid only when the charges are static. We don't know whether it is valid when the charges are moving or when the charges are accelerating. That we will study towards the end of the semester. And it turns out that the Coulomb's law is not valid if the charges are moving or accelerating. And the end result of which is that, for example, if I have, let's see, if I have one charge over here, let's just take a single charge, Q, it creates an electric field over here. And if the charge of the, if Q is positive, what will be the direction of the electric field? Right-hand rule. You like that? Huh? Away from the charge, right? If this is positive, this will be the electric field. Now, if we just displace this charge, let's say if we just move it here, for some time, the electric field here will still stay in the same direction for a very short amount of time. But eventually, the electric field here will also rotate in that direction. Now, how much it takes? Well, if this distance is d, the amount of the time that it takes for this electric field to change its direction is d over c. C being the speed of light. So this also kind of tells us that this law, this definition of the electric field, does give us a local description of the theory. Because what happens is, if you have an electric field, let's look at this picture. Initially, the charge was over here. We have some distribution of electric field in all of space. Now, when we move it over here, let's say I am the charge, there's an electric field created at the position of Sercan, and when I move to this step, the first thing that changes is the electric field in my near vicinity. That change in the electric field in my near vicinity is in fact what creates a change in the electric field in the next step, which changes the electric field, Eventually these changes reach the point of Ercan where the electric field at the point of Sercan changes. And Sercan only feels the electric field at his point. You will feel a force if you are charged. Other questions? And not this year, but in your third year, you will see that this electric field, changing electric field, carries a momentum, linear momentum. They have linear momentum. They have energy. They have angular momentum. So they have all the properties that we assign to point particles, point masses in the mechanics course. Yes. Now, in all physical sense, it exists. It has all the properties of any matter. So although, I mean, this semester, until the end, until the last weeks, let's say, it will just stay there as a mathematical construct just to help us in our calculations, but we will see eventually that it's a real thing that has a physical existence on its own. Other questions? Now, so we have the charges, we know how to define the electric field. I mean, another way of, okay, we define the electric field mathematically, but you can also talk about how we can measure the electric field. So if you look at here, the electric field at the point R1 is nothing but the force act. If we put some test charge at that point, this will be the force that it will feel divided by Q. This is how we can measure the electric field. Or you can say this is another definition of the electric field. So we just take some charge. If we want to measure the electric field at the point, let's say R, we just put some charge there, measure the force acting on the charge, divided by the charge of the charge that we placed over there, and just do this for very small charges. Now, the reason why we consider only very small charges is that, for example, if you have, let's say, we had already seen that if we have a conductor, a neutral conductor. Now, what is the electric field at this point? What do you guess? The electric field at that point. The conductor is neutral. Its direction, or you can even say a number. It is zero. There's no charge anywhere. So the electric field here is zero. So if we put some test charge over there, any charge, it shouldn't feel any force. Since the electric field is zero, we know that the force is the charge times the electric field. If we put any charge over there, it should feel zero force. But what happens if we put a charge? So we have the same place. We put some charge over there, let's say a positive charge. Will it feel a force or not? In which direction? Or let's do two examples. We put a positive charge and a negative charge. Will it feel any force? I mean, before we said that at this point the electric field is zero. And at the same point, we are putting a positive charge and a negative charge. Will it feel force or not? These are the charges. Yeah, I have this conductor, neutral, and we just said that there is no electric field at this point since it's neutral. So in principle, if our definition of the electric field is right, then we should say that, okay, if the electric field is zero, if you put any charge there, the force is the charge times the electric field, so the electric field is zero, so the force should be zero. Naively, one would say so. Is it true or not? If I put a positive charge here, will it feel a force or not? It will feel an attractive force. The negative charge? No, so you are saying that both of them will feel an attractive force. Now let's see what will happen. Now this is a conductor. And since it's neutral, we said that the electric field is zero because at every point there are positive charges and negative charges in equal amounts, equal densities. So if one creates an electric field at this point in this direction, the positive charges, the negative charges will create an electric field in the opposite direction, so the net electric field will be zero. But if we bring a positive charge, positive will attract the electrons which are free to move inside the conductor. So there will be more electrons here and less electrons on the other end. So we have the negative charges, we have equal amount of positive charges on the other side. Well, the charges are in equal amounts, but the negative charges are closer than the positive charges. So the force that these negative charges create will be larger than the force that these positive charges will create. And hence, the negative charges is attracting positive charges. So this object will feel an attractive force. A similar thing will happen over here. This is a negative charge, so it will push negative charges inside my conductor. So I will have negative charges accumulated on the other end, and positive charges will be accumulated over here. Well, positive charges are closer to the negative charge, so they will create a larger attractive force. So the net force will again be attracting. Now, the problem over here is that if we calculate this force and divide by the charge Q, we will get the electric field. But it will not be the electric field of this system. It will be the electric field of this system in which the negative charges are on one side and positive charges are on the other side. So if you put this large charge, the larger the charge is, the larger the deviation of my system from the original system would be. So if I want to measure the electric field, I have to make sure that I'm not changing my system. And one way to make sure that I'm not changing the system is to make sure that I'm putting a very small charge. The smaller the charge is, the smaller its effect on my system will be, and hence the smaller the change in the electric field of my system will be. So what I obtain there will be the closer Q is to 0, what I actually measure will be closer and closer to the actual electric field of my system without the presence of this charge. Any questions? What kind of a change do you expect? So let's say we have some holes over here. And if I put a charge over here, I have this system. And I can also consider the system in which I don't have that hole. In which this is also filled. The electric field here. Will it be different or will it be the same? Well, let's discuss it in a moment. I mean, we can discuss some of it today, some of it next week. Now, one problem is how do we visualize the electric fields? Remember on mechanics courses, we were always drawing this free body diagram to simplify, to kind of visualize the processes. Now, how do we visualize the electric field? So if you, let's say you imagine some charge over here, positive charge. Now the electric field here, I remember the definition of the electric field is 1 over the, let's call it Q prime. I'm just placing some test charge somewhere. Limit as Q prime goes to 0. Of the force that this charge will feel, and this is limit as Q prime goes to 0, 1 over Q prime, 1 over 4 pi epsilon 0, Q prime divided by R squared in the radial direction. And this Q prime, they just cancel. Nothing depends on Q prime anymore. So the electric field of a point charge is 1 over 4 pi epsilon 0 Q over R squared. This is the electric field of a point charge. Now, so what do we see? This is just a constant. So the electric field of a positive charge is always radially outward. It decreases with the square of the distance. So if you double the distance, the magnitude of the electric field becomes 1/4 of its original value. So if at this point, this is my electric field, at this point, this will be my electric field, or at this point, this is my electric field. At this point, this will be my electric field. Well, this is one way of showing the electric field. We can just draw vectors at every point, or at a selection of points. I cannot measure the distances here. Let me just. It is shorter now. Well, things get messy. So this is usually not the way we show the electric fields. So what we use is what we call the electric field lines. Now, if you remember our discussion in fluid dynamics, there also we discussed about the streamlines, which were basically if you just follow one piece of the liquid, you just draw its trajectory. It will be your streamline. So just like that, here we have the electric field lines. These are lines that are tangent to the electric field vector at every point. So in this case, these will be the electric field lines. Now, two properties are important. Now, if we want to specify the electric field, which is a vector, we have to find a way to visualize two things: its magnitude and its direction. Those two things we have to show somehow. Now, the direction is easy to show with lines. So because if you imagine any line, it has a tangent direction, and that tangent direction tells me the direction of the electric field lines. That's why I also put these arrows. So for example, if in a region of space, this is the electric field lines, at this point, I know that the electric field is in this direction. At this point, I know that it is in this direction. And at this point, it's in this direction, etc. So drawing these lines such that they're at every point, the lines are tangent to the electric field at that point, I can just use these lines to show the directions of my electric field. Now, another thing is, what about its magnitude? Now, any questions about the direction? So I'm drawing these lines such that at every point, they are tangent to the electric field line. That is the property of these field lines. So since they are, by construction, tangent to the electric field, at a given point, you just find the electric field, the tangent to the electric field line passing through that point. That gives you the direction of the electric field. The second property is, what about the magnitude? Now, for the magnitude, just make this observation. We know that this is the electric field. Let's take this one. And let's multiply it with 4 pi r squared. Well, 4 pi r squared, does it remind you of anything? That is the surface area of a sphere. This is equal to Q over epsilon 0. Now, in particular, it is constant. For a given charge, it is constant. Now, let's imagine these electric field lines. Of course, just imagine it as if they are circles, in 3 dimensions, sorry. So I have these electric field lines moving out in all 3 directions. Their numbers are constant. So if I imagine a sphere, such a sphere of, let's say, radius r1, and if I imagine a larger sphere of radius r2, so how are the densities of these field lines passing through these surfaces related? The density of field lines, that is the number of field lines per unit area. Well, the number is constant. Density of field lines. This is equal to number of field lines divided by the area. Well, the number of field lines is a constant by construction. the area of the sphere is 4 pi r squared, so the density of field lines is proportional to 1 over r squared. Just like our intensity of the electric field. So we can say that, okay, the electric field lines have two properties. They are tangent to the electric field at every point. So if you want to find the electric field at a given point, you just find the electric field line that passes through that point, draw the tangent to it, that gives you the direction of the electric field line. Second, their density is proportional to the magnitude of electric field. At least that's kind of trivial to see in the case of a single charge. The density of field lines is nothing but number of field lines divided by the area. The number is just fixed. We are not changing that. The area is proportional to 1 over r squared, so this density of field lines is proportional to 1 over r squared, but 1 over r squared is nothing but proportional to the electric field at every point. Now this proportionality of the electric field line density to the magnitude of the electric field is valid in general for every system, independent of how many point charges you have. Now let's do some examples. Well, we already did a single point. Let's imagine we have some positive charge over here, some negative charge over here. What will be the electric field at every point? Now we already know the superposition principle for the forces. The force at any given point will be nothing but the force created by the first charge, the force created by the second charge, etc. So you just sum the forces that each point charge making your system creates. Well, the electric field is nothing but the force created divided by the charge, so the same principle will also hold. It's electric E1 plus E2 plus etc. Now we already know the electric field of a point charge. Now we have 2 point charges, one positively charged, one negatively charged. Now we can talk about the electric field at every point. Now let's just choose some sample points to get an idea about the direction of the electric field line. Now at this point, what is the direction of the electric field? Well, why do you think it is 0? It's not, okay. So what is the electric field created by this positive charge? It's in that direction, towards the right. What is the electric field created by this negative charge? Negative charge. It's still in that direction. You see, okay, this is the electric field created by a point charge. Now, 1 over 4 pi epsilon 0 is a positive number. 1 over r squared is a positive number. R hat is a vector that is pointing away from our charge. So if you forget this charge q, what remains is a vector that is pointing away from my charge. So if q is positive, then this whole expression, well, let me write it like this. This is equal to q times 1 over 4 pi epsilon 0 r squared in the r hat direction. Now this whole thing is a vector that points away from my charge. If Q is positive, if I multiply this vector by a positive number, its direction will not change, only its magnitude will change. But if Q is negative, then its magnitude will change and its direction will change. So if for a positive charge, the electric field created by a positive charge, it is pointing radially outward. If I put some positive charge over here, the electric field and hence the electric field lines will be like this. If I have a negative charge, the electric field lines will be radially inward. How many electric field lines do we have? Well, it's up to you. You can just draw as many as you like. Now, how many electric field lines you draw will mainly, I mean, here we are saying that the density is proportional to the magnitude. And this proportionality constant will depend on how many field lines you choose. If you double the number of field lines you have, then the proportionality constant will be halved. Or if you reduce the number of field lines by 2, then the proportionality constant between this density and the magnitude will be just multiplied by 2. The density of the electric field lines is proportional to the magnitude of the electric field. No. Density is number over the area. You don't. You just draw some sample lines. For example, here, I just prefer to draw 5 of them. No, you don't have gaps. At every point, there's an electric field line passing through that point. The number that you draw. I mean, in reality, there's an electric field that, if there's an electric field at every point, then there's an electric field line that passes through that point. But although the electric field has a physical meaning, it physically exists, the electric field lines do not have any physical meaning. They are just tools that we invent just to visualize the electric field. Now, in this case, for example, at this point, there is no I didn't draw any electric field line, but it doesn't mean that the electric field there is 0. So let's come back to this example. Well, here I have some positive charge. I know that the electric field created by this positive charge is radially outward. So it will create an electric field at this point toward the negative charge. And the electric field created by the negative charge is pointing down inwards. So again, the electric field created by this negative charge at this point will be in the same direction. So the net electric field will be in this direction. This is independent of which point I take along this line. For all the points along this line between these two charges, the electric field will always point from the positive charge to the negative charge. But by construction, the field lines are always parallel to these vectors. So I can draw one electric field line that goes from the negative charge to the positive charge in this direction. Now that is one electric field line I have. Okay, let's look at that one. Let's choose this point, for example. Now the electric field created by the negative charge at this point will be in which direction? It will be towards the negative charge, so it's left. The electric field created by this positive charge at this point will be towards the right. Which one will be larger? Well, they both have the same charge, but the negative charge is closer. So at this point, the electric field will still be in this direction. And this will be true for any point along this line. So electric field along this line will be just straight again, but it will be moving towards the negative charge. Well, if we do the same thing on the other hand, let's see here, the electric field created by the positive charge will be towards the left. The electric field created by the negative charge will be towards the right. But the electric field created by the positive charge will be larger because it is closer to my point. And hence the net electric field created at this point will be pointing towards the left. It will be true for every point along this line, and hence the electric field at that point will be, electric field line will be along this line. So this was kind of the easy part. This is the electric field lines along the line connecting these two charges. Now let's look at some other point. Now first let's look at these points. The electric field at this point. The net electric field. Well, what is the electric field created by the positive charge? Away from the positive charge. So let's see, this is E1, let's call it. The electric field created by the negative charge, it will be towards the negative charge. What can you say about the magnitudes of these two forces? E1 and E2, are they equal? Some of them is larger. Or we cannot say anything about the magnitude. Well, let's see. What we know is the electric field magnitude of a point charge is Q over 4 pi epsilon 0, 1 over r squared. Now, by the way, this line, I forgot to mention it. This line is midpoint between the positive charge and negative charges. So this distance is equal to this distance. So in such a case, this distance, the distance from the positive charge and the distance from the negative charge, they are equal. So r is the same. This r is equal to this r. This is constant. This is the same. This is just a constant. This is the same for both of them. So the magnitudes are equal. Only because this line just goes in the through the middle of these two charges, and is vertical to them. So if you just sum these two vectors, you will get a horizontal electric field. Now the electric field at this point will be horizontal. In fact, this will be true for any electric field along those lines. So when you draw electric field lines, you have to make sure that the tangent to the electric field lines along this line should be parallel, horizontal. Okay, that is another thing we know about the electric field lines of this system. Now let's look at one other point. Let's consider points very close to our positive charge. They are very, very close to the positive charge. What can you say about their direction? So you are saying that this negative charge will have no effect at that point? Is that what your claim is? Now we know that the positive, if you had a single positive charge, we know that the electric field lines are radially outward. Now my question is, okay, I have a positive charge over here, but there's also a negative charge over here. But nevertheless, I'm looking at the points very, very close to my positive charge. What can you say about the electric field lines at those points? Are they radially outward, although I have this negative charge? Your friend says yes. Anybody else? supporting him, challenging him. What can you say about the magnitude of the electric field lines very, very close to this point? Almost infinity. Why? Okay, R is going, for these points very close to this point, R is very small, so the electric field created by the positive charge is almost infinite, as your friend points. What about the electric field created by this minus charge at those points? Not necessarily zero, but finite. Not too large, not too small. So you have something that is almost infinite. You add something that is finite, not necessarily small, but definitely not very large. But in that case, that finite thing doesn't contribute. I mean, it's negligible compared to almost infinity. So that is another thing that we know about the electric field lines. They should be very close to this point. They should be radially outward. Of course, as you go away from that point, they will no longer be radially outward, but very close to this point, they have to be radially outward. So let's see, these are some more, at least the beginning points of some electric field lines. What can you say about the electric field lines very close to this minus charge? Zero? Why do you think it's zero? No, infinite is infinite. It's far from zero. Well, again, the electric field created by this negative charge will be almost infinite since I'm very close to that minus charge. So the electric field created by this positive charge will be negligible, very close to this negative charge. But if I ignore those effects, the electric field of a negative charge is radially inward. So I also know that the electric field lines very close to this charge is radially inward. Well, let's look at this point. Let's take some typical point over here. What can you say about the electric field line there? Will it be horizontal? Why not? It's closer to the positive charge, so the electric field created by the positive charge will be larger. Well, that also tells me that it will be somewhat pointing away from the positive charge. So the electric field electric field at that point will be more or less in this direction. Somewhat. Well, this kind of gives me an idea already how the electric field lines should look like. They should start radially outward. They should bend towards the minus charge. When they reach this line, they should be horizontal. And then they should bend towards the minus charge, negative charge. And when they reach the negative charge, they should be radially inward. So if you just draw the electric field lines, they should look something like this. So let's also cross this one. This is how the electric field lines should look like. This is more or less the shape. So you see, the electric field lines are strongest here. The density, the densest over there, those are the regions where we have a strong electric field. This one and this one. These regions are regions in which the electric field lines are not so dense. So the electric field in those regions are smaller. Any questions? So as you go away from along this line, the electric field gets weaker and weaker. Also, as you go along this line, the electric field line first starts to get weaker until you reach this point. When you reach this point, after this point, the electric field magnitude gets larger, so the electric field gets stronger. So by just looking at this the diagram of the electric field lines, we can see the regions where they are strong, regions where they are weak. So it helps us to visualize. Any questions? Okay, a 10-minute break.